Yes, as you can see, today we have Trygve that will tell us about the frame flow categories and spectra instead of Alice.
Okay, thank you. And I mean, we're now 4 people here, so ask questions, right? There's literally nothing stopping you. Right. So what do I want to do? I want to give us a quick reminder on flow simplices, because they were kind of appeared at the very end of the previous lecture. So maybe we can get a little more of a feeling of what the flow simplex actually does. And then I'll summarize the second half of the Abusad-Blumberg paper, arguing why, or seeing how they construct an infinity category, and arguing why this is a stable infinity category and why it's in particular equivalent to spectra. So a couple of caveats today, if you maybe in particular if you're trying to follow along based on the Abusad-Blumberg paper, is that today I will be considering manifolds only. So I might write the orb, but it's going to basically mean manifolds with corners. So just assume that this group of these isotropy groups are trivial everywhere. And that makes some things a bit simpler. The other thing that will matter basically only at the very end is that I'm taking this this monoid that they're talking about to be 0. And that is also what we did last time. So hopefully there's no confusion there. Okay, so let's remind ourselves what the flow category was in this setting. So what the 0 simplex in this. So far we have like a semi-simplicial set of flow simplices. So the 0 simplices are flow categories. So what I think of when I think of a flow category is that I have a set of objects that I'll denote with a capital P. From this set, I can form the indiscrete or chaotic category. This is a 1 category whose set of objects is also P, and there's exactly 1 morphism between every object. The good thing about this category is that it's very good at capturing enriched categories whose set of objects is P. So in particular, I can take these 2 categories that we talked about last time that control the stratification. They are now lax functors. So like this is a lax functor into the monoidal category of these models for manifolds with corners. So it's like a specific, maybe I'll write categories with corners like this. So it lands in a very specific type of categories. I'll use the name AP for this 2 category. I know that Abusad and Blumberg just use the letter P again, which I find to be a bit confusing. So A for arc is my notation. So this is we'll see what I'll give you a reminder of what this 2 category is later, but yeah. So the thing is that a category enriched in the monoidal category of categories, that's exactly what the 2 category is. So a lax functor out of this into this is a category enriched in this. Now over this guy, we have the 2 category, the orb framed. And this has something like a 2 functor to the monoidal category, which just records the underlying stratification of orbifold with corners. And I mean, the 0 cells up here, right? They're vector spaces, and they are just collapsed to the single 0 cell down here. And then all a manifold with corners or orbifold with corners is collapsed to its stratifying category. Then the definition was that a flow category was a certain lift. So it's something like this. Here is your X. It's a category with set of objects P enriched in this 2 category. So in particular, if we try to unwrap what that means, it means that for each little p in P, you should get the 0 cell of the 2 category up here. And the 0 cells were virtual vector spaces. Right? And then we need to say what this functor, what it does on this Lex functor, what it does on morphisms. So remember that there's a unique morphism between the point P and some other point Q, and that has to be mapped to some object of one of these d-orb framed, like a one cell in there. So I'll write that as for each pair PQ, we have some derived orbifold X PQ. It lives in the mapping category between the objects VP and VQ. So in particular, it's a manifold with corners with some tangent data that I'll come back to later. Now we need to see that it's a lift of this guy. So that means that if I just remember the stratifying category, which we denoted like this, then this should be isomorphic to this arc category. And in this particular example of flow categories, this had a maximal object, which is this very simple arc, just starting and ending at Q. And then for every other object in this set, there's a codimension 1 stratum, which is called something like PRQ. And then maybe I could have some different Rs, like give me a different codimension 1 strata of this kind. I could break at multiple things, but these are all the boundary strata of XPQ. Right. Now this is a lax functor, so that means that composition isn't on the nose, but it's up to a 2 cell. So that means that if I take the 2 cell that I get from, or the 1 cell that I get from P and Q, and I take like the product or the horizontal composition with a 1 cell that I got from Q and R, I don't want this to be equal to the 1 cell that I got from P and R, but I want there to be a morphism connecting them. That's what lax means, right? We don't have this composition on the nose, but we have a composition up to some maybe non-invertible 2 cell. And in fact, it's always going to be non-invertible here. This is a morphism in this pretty strict category of manifolds with corners, where in particular it's a certain stratum inclusion. So these kinds are actually always going to be codimension 1 stratum inclusions. So it's going to be a diffeomorphism onto some connected components of the codimension 1 boundary of this guy. There was also some more data. Remember that this 1 cell up here actually came with some vector bundle that was denoted EX and some decomposition of that guy. So it was decomposed into some U, PQ. And I don't think we mentioned this last time, but this is forced by the definitions of Abusad and Bloomberg to be equal to the virtual vector space 0 R to the Q. And this represents quotienting out by translation. That's what this R factor does. And we'll see exactly why in a minute. And this virtual vector bundle E should also have a part called I. And because I'm in the frame setting, I want to require this to be 0. Now the condition, or like the data that you want on the tangent bundle, is that the tangent bundle of X PQ, it should be VP minus VQ minus, or I guess actually plus this U, but since the U is like a minus R, I'll just write this as minus R to the Q, and maybe plus some stabilization, so like a W comma W, something that's trivial on K-theory. And this is like a very familiar equation in Morse theory, right? If you put this R on the other side, you're saying that before quotienting out by translation, your moduli space was an intersection of the unstable disk at the source with the stable disk at the target, up to some stabilization maybe. And then there's also one more condition that we didn't talk about last time, which is going to become important at the very end today. And it's a condition that for each fixed p, I can take the union over all xpq, and I want this to be compact. The way to think about this is basically to sit down and think, what do I need to define like the Morse differential of p, right? If I want to write something like the Morse differential of p, well, I should sum over all q the number of like xpq, and I want this to be a finite sum, or else my algebra is kind of going to break down. So like the analogous thing here is to require that this union is compact. That guarantees me that I have a well-defined Morse differential and like whatever higher analog you would want of that.
But just to make sure, you
Yes.
require that. So if you require that for all p's, not only for p with such that the index of p is the index of q minus 1 or something like that.
Correct. I require this for all like for each fixed p, I require this for the union of all q in p.
Mm-hmm. So, for example, the category is like z points. Like can't have that. All of them have. Okay. Yes.
You can't have non-trivial, non-empty moduli space everywhere.
Thank you.
Only a finite number, and this is going to be important later. Okay. This is a lot of stuff, right? And I guess technically we should also add that there's some coherence of all these types of data, in particular like the like how we have these isomorphisms of the tangent bundles and like associativity of these composition maps and so on and so on. But I guess you can kind of imagine what that should be. And this looks like kind of a more like roundabout way of formulating what the flow category is. Like we had a good definition of flow category already like 4 talks ago. But the big selling point of this this type of structure is that now if I want to define a flow n simplex, I replace my p, my set p, with some sequence of sets. So this, you should now think of a flow n simplex whose n+1 corners contain flow categories whose set of objects are indexed by each of these p's. Then I can again make some kind of enriched object. So now it's going to be not quite an enriched category, but something like it. But the set of objects is going to be just the union of all the pi's. There's a slightly more complicated stratifying category called a p vector, but it still goes into this monoidal category of categories with corners. And the orb framed still lives up here. And a flow n simplex is a certain lift like this. So the perk is that we're now able to define what the flow n simplex is for every n in a uniform way without having to write down this type of list of data every time, which is very good. And it gives us a semi-simplicial set of flow n simplices. So examples of flow categories that will show up in this talk are the 2 very trivial ones. We have the empty flow category, which is the unique thing on the empty set. No objects, no moduli spaces. We have a flow category that I will denote by 1, which is a flow category with 1 object and no manifolds. Abuside and Blumberg denote this by a star, which makes me irrationally angry, because that's usually reserved for a terminal object. And this guy is not the terminal object. So I refuse to use that notation. Other examples of when this will show up is if you have a Morse function on a closed manifold, you can do the Morse theory and get your flow category. And of course, this is where you also see some equation like this again. And what they also show in the paper is that you get this kind of structure for Hamiltonian Floer theory. I guess if you want manifolds, you should assume aspherical. This guarantees you that you actually get manifolds and not orbifolds. And if you want frame, you should have some assumption on the tangent bundle. But roughly speaking, we now know that Hamiltonian Floer theory will produce something like this. Good. And what's more, like the definition of a flow simplex is made so that up to equivalence in this category that we get later, this guy is well defined independent of choice of Morse function, and this guy is defined well defined independent of all the choices you make when you do Hamiltonian Floer theory. So there's a choice of complex structure, maybe some perturbations, all of this, and it's independent. The equivalence class is independent. Okay, so let's. I don't think. I mean, we've seen a lot of different. Yes.
Oh, just to make sure, the example, if I have a framed manifold, I still can have the category with two objects and this manifold as a morphism.
Yep.
And do we require some restrictions on the dimension of the manifold? Like if my points, oh, there is no index yet.
But this is a very, very good question, Nadia. And actually, there is no index, but we have kind of enforced a dimension formula already. Because if we look at this equivalence of virtual vector bundles, the dimension has to be the same on both sides. This W minus W has virtual dimension 0. This has virtual dimension -1. And this has like virtual dimension of this minus virtual dimension of this. So I guess you could actually say that, yeah, we already have a grading where the grading of an object is like the virtual dimension of the VP. And then every flow category has to satisfy that the dimension of XPQ is equal to the grading of P minus the grading of Q minus 1. So these are in particular graded flow categories in the sense we maybe saw earlier.
Great.
And this is, of course, important here that I picked this to be 0. I think it's a bit unclear in the paper whether they mean 0 or whether they mean some trivial vector space. And if you choose this, you get something very different. Then you get an ungraded version, which is somehow more confusing. So let's stick with 0. I think that's how you get spectra. Good. We already saw what a flow by module is. And essentially the one simplices in like a flow one simplex is basically a flow by module in the way we've already defined it. But the thing we haven't seen yet are what the higher simplices do. So let's look at the particularly nice and easy two simplex. A two simplex, I mean, it should have 3 edges and 3 vertices, right? So I'm gonna try here to write down what the two simplex that fills a diagram that this could be. So I'm gonna have the flow category with 1 object here and here. And I'm gonna have some flow category with 2 objects and 1 manifold between them up here. And we're gonna have some flow by modules. So I guess what we need to do then is to look at this sequence of sets and try to write down what the objects of this stratifying category is. And the most interesting stratifying category is going to be the one that's valued at this point and this point. That's the one that kind of captures the maximal stratum. So this has a codimension 0 stratum, which has this kind of label. So it has this label by this set up here. So like this This is 0, this is 1, and this is 2. So because this vertex lives between something labeled from set 0 and set 2, it could potentially have a label of 1. And I'm going to choose the stratum that has a label 1. And this is going to be like the interior of my two simplex, the thing that lives here. So maybe this is called something like age PS. This is like the biggest manifold that appears here. How can this break? Well, one way it can break is that this label here can disappear. We can label by the empty set instead. I'm just going to drop empty set labels, so it has a label like this. This corresponds to what we should call DPS. So removing the 1 means that I'm no longer allowed to have some breaking in the flow category at vertex 1, which is this vertex. And that means I'm just going along this lower boundary here, which is where D lives. So this is DPS. And of course, this is codimension 1. And from here, I can't break any further. This is now a closed manifold. But if I go back up here, this could break in different ways. Because as long as there's a 1 up here, it means we're allowed to break somewhere inside the flow category X. So there are 2 options. I can either break at the point Q, giving me an arc that looks like this. This also has codimension 1. And what we should think of this as labeling is the product BPQ times X times CQS. And likewise for R, I could also break there. And we could have something like PRS, and that should be BPR times CRS. And there's one final guy of codimension 2, which occurs if I'm breaking both at Q and R. So this is an arc with 3 vertices, and it's PQRS. Technically, I guess you could also have like the order here swapped, but only one of them is going to be non-empty, or at most. So let's just assume that Q has the bigger index. And then this is going to be something like BPRQ times XQR times CRS. And of course, you can see that this stratum is particularly the intersection of these 2 strata. So what this kind of tells us is now that this DPS, this is closed. And H is something which is a cobordism from this closed manifold to something which is not quite a closed manifold anymore, but something which is like 2 manifolds with boundary meeting in a common boundary.
Wait, a bit confused. So why DPS is closed?
There is no more breaking for this guy. This can't have any more
yes.
boundary strata.
Okay. Yes.
And I guess in this particular thing, you can see that actually has to be a 0-dimensional manifold, because that's just what the index tells you. So maybe this would be more interesting if I wrote something like this. But let's get back to that later.
Oh, so if I want to imagine, okay. It's clear why the index of P and the index of S are the same?
No. It's not clear.
Okay.
Later, I think I will use one specifically to refer to one object in index 0.
Mm-hmm.
Yeah.
Okay.
But for now, I didn't say so yet. So. Okay, so this is a 2-simplex. They're a bit like bordisms, but they're bordisms between something which is a flow by module, in this case a closed manifold, and something which is like a broken thing, like a formal composition. And this is not this formal composition is not a manifold with corners or a flow by module in its own right. It doesn't have the right boundary structure. But what this two simplexes is capturing is to say that the composition of B and C up to cobordism is D. So I guess in particular, if you looked at how compositions were constructed in the Porcelli-Smith paper, this is an example of that, where you take this formal composite and you thicken it up a little bit to get the bordism to something which is actually a bimodule. All right. Now that we've gotten maybe some more intuition for what these simplices are, let's consider the category or let's try to get the category from this. So right now we only have a semi-simplicial set. I'll denote this with a little plus, meaning that I only have the phase maps, or only the injective maps between ordered sets, not the degeneracies yet. And the value of this at n is the set of all flow n simplices. And of course, here you can see actually how to consider one of these phase maps to for instance get this phase D and just restrict to only like the subcategory with things that are labeled by forgetting all labels that came from the set 1, P1. So if I just look at all the strata that are not labeled by anything with Q or R, and which does not have this label 1 appear, then I'm going to see D1 of this two simplex. But we would really like for this to be a category, an infinity category. We would want it to have horn fillers. We would really want it to have the degeneracies as well, but as it turns out, it's going to be kind of easier to do the horn fillers first. So maybe you should think of this as saying that we're saying that we're building like a non-unital category of frame flow categories first. So this does indeed have horn fillers. Proving it is a bit technical, but let's see like the idea of how it works. Let's say that I have some horn like this. That's a map from the Kn horn, considered as a semi-simplicial set, and a map into flow frame. That's going to be some diagram of flow n-1 simplices fitting together in the way you expect. And what you can kind of argue is that this is going to, like if this is called Y, this map here, this is basically going to be, well, it at least has to specify, because we're hitting all the vertices, it has to specify, at least it has to specify all these objects. So it specifies some sequence of sets that form the objects of the flow categories you see at the vertices. And the only thing we're kind of missing from our description are like the maximal phases of that should live between some P in P0 and some R in Pn. And I don't have all the data of writing down what kind of YPR should be yet. All I have is that YPR defines something like a functor from a category that we can call lambda nk a p vector PR. So this is just a subset of this stratifying category where I have forgotten where I just removed the labels that shouldn't be included in my horn. So in particular, if we go back to this example here again, I could try to do the horn, the 2-1 horn, of a P PS, and then I should remove this guy, because this is like the maximal thing, the interior of the simplex. And I should remove this guy, which is the bottom edge. So in particular, I think it's quite easy to write down a formula for exactly which places that you are not allowed to touch, basically. And you have a functor from this into the orb frame. Not quite, because this is a 2 category, but something very close to this. And it's basically by this type of formula that we wrote down over here. And you can see that it's going to be a functor. What I would really like to do is to just take the co-limit over all this, to glue these together. Manifolds, smooth manifolds are not that nice with co-limits. But what's certainly true is that as a topological thing, this co-limit makes sense. Basically because this indexing category looks like a topological manifold itself, I can take this co-limit as a topological manifold. And even more, this stratifying category looks a lot like a manifold with corners, because it is a model for manifolds with corners. And this is the fact that allows me to say that I could actually smooth this out, like thicken it and smooth it. And in of itself, that is maybe not so hard to do. The hard thing is doing this coherently over all PR simultaneously. But that is what the composition does. And Poseidon and Bloomberg write down some machinery for doing this that I'm not going to go into. But the idea is that they create coherent smoothing of all these topological manifolds. Good.
Can you repeat why is the reason, like what property the horns satisfies as an indexing thing, so this machinery can work?
It's not very clear, but I think this would not work if it weren't for the fact that this guy is a model for manifolds with corners, which means that its codimension k strata are precisely specified by the intersection of k codimension 1 strata. It has this like very nice combinatorial property, which I think is essential for this smoothing procedure to work.
Mm-hmm. Thanks.
I think we should think of this poset as like describing something like a PL manifold, and we're saying that it's actually like a smooth manifold with corners. Yeah. Good. So that kind of tells us that we have something like a non-unital infinity category. And before we get on to specifically how to construct the generacies, maybe let's go to a small philosophical point, which is that as soon as you have a non-unital category, it's more of a property than extra data to have identities. You could just look at the set of endomorphisms of each object, and you could look in there and you could see how a fixed object behaves with respect to composition. Like what is the push-forward morphism of that guy? And if you can find for each object something that looks indistinguishable from an identity morphism, then you're in business. Then you could actually just say that, okay, my category is, my non-unital category is actually just the underlying non-unital category of a unital category. And this shows up in infinity categories in a couple of different ways. So one way is the theorem that Abusad and Bloomberg use in this paper. There is also this notion of quasi-unital semi-Siegel spaces as a different model category presenting the infinite category of infinite categories. So yeah, this is like a bigger principle. So as soon as we have a category, we actually don't need to construct all the degeneracies. We just need to show that each object has an endomorphism that behaves like an identity. And we can try to start doing this for some flow category X. What I would really want is that I would want the moduli space connecting some object in X to itself to just be a point with positive framing. Because that's what it should be in Morse theory, right? I should just see the identity. Or in homology, I would just want to see the identity. Let's try to write down what the boundary of something like this should be. If I take some other space occurring in some endomorphism like this, it should at least contain as part of its boundary spaces like this. Either I break on the right-hand side, X, not this, but this, times X PQ. And it should also contain whatever happens if I break on the left-hand side, which is S X PQ times SX QQ. Now, if I wanted this guy and this guy to be a point, then I know that I at least need like 2 copies of XPQ in the boundary of SXPQ. And this gives me a nice idea. What if I just took SXPQ to be a product with the interval? This definitely has these 2 guys as part of its boundary. So let's write down, this also has like a boundary, right? This has XPQ and XPQ. So it's like 0 and 1. But the problem is that on the left-hand side, we kind of have more things. If I break at some different object, we could have something like SXPR times XRQ, and something like XPR times SXRQ. And if both of these guys were intervals, something would go wrong. Right? If I'm continuing with this pattern, I'm kind of now saying that as part of a boundary of this interval, I'm seeing both the interval times XPR times XRQ, and I'm seeing the same thing again, XPR times the interval times XRQ. One of these guys fit in the boundary of this guy, just from going to the boundary of a product is going to the boundary at either side. So if I only go to the boundary in XPQ, I'm going to see this stratum. But 2 copies, that's too much. They don't fit. And the more objects I have, the worse this problem gets. There are kind of more and more strata that I'm not accounting for if I just do this kind of naive interval model. So that doesn't quite work. You have to do something more complicated. But the upshot is that it's not so bad, right? We're not that far off, actually. It's just a problem that this breaking gives you multiple copies of the same thing. I guess the reason that this happens has to do with the fact that when you go to some kind of boundary, you're kind of modding out by this R translation twice, while in the interior, you're only modding out once. And what we would really like to do now is to try to invert that operation. And if you're at a very, very broken thing, you've modded out with R translation many, many times. And then you kind of have to invert that deeper process. So the way to do this is, I mean, again, it's a bit technical. I'm not going to go through it all. But the thing you do instead of just taking the interval is taking one parameter family that looks like this. So it has one open end and one closed end. At the open end, it's just something like an interval. And then it kind of gets more and more curved. And at the very end, it's two versions of the interval meeting in a corner. Now, if you imagine that you have some manifold with boundary, and you let this direction, this interval here, parameterize a normal direction to the boundary, so that this is like x, and then the boundary of x lives over this boundary. You can use local charts near the boundary to make this picture global, and take something like a total space of this family over your manifold. So that over the interior, you're actually just seeing x times the interval, but over the boundary, you're seeing x times 2 copies of the interval meeting in a point. And then you have to do iterated versions of this, and you have to iterate it more and more times when you have deeper and deeper corner strata. But this is the construction that they pull off, and they're able to construct this Sx, which is an identity morphism. And the way to see that it acts as an identity under composition is to not only construct S, but to construct morphisms S0 and Sn that go from the set of n simplices to the set of n+1 simplices, and which satisfy the identities you would expect the 0th and nth degeneracy to satisfy. And basically what that is telling you is that composing with Sx on the left or on the right acts as a homotopy equivalence on the mapping space. And that tells you that your potentially non-unital category had something which looks identical to units all along. And so we can actually upgrade it to a quasi-category, which extends your original non-unital version. Good.
I mean, just to make sure, I wonder, you try to construct the identity map in this category, and okay, I think that maybe I need to think about it a little bit more, but I'm not seeing intuitively like why you can't multiply all your manifolds by intervals. Okay, never mind. Yeah.
Yeah, so I think that this is the example to keep in mind. That
Yeah.
Yeah.
Somehow, yeah, things not compared, but never mind. Let's continue.
Yeah. This one is a bit, it's not super intuitive. I don't love it. It's like a kind of annoying thing about this category, that the identity is so weird. You know, it would be much nicer for the homotopy theory that we're going to do later if the identity was kind of easy to describe, but it's not. Right. So we have an infinity category. We would love to show that this is actually a stable infinity category. We're going to do this in 2 steps. We're going to show that it's pointed and that it admits suspensions, and that suspension is an equivalence. Like the functor that takes an object and sends it to its suspension is an auto-equivalence of our infinity category. And then we're going to show that our category admits all cofibers. And these are like pretty much orthogonal, these 2 proofs. So let's start with pointedness. The empty flow category is the base point for our category. Why is this the case? I'm gonna kind of sketch it very, very briefly here. Let's say that we had something like, could there exist 2 different maps from the empty flow category to some other flow category X, given by like 1 cells like this? such that there is no way to fill this to a two simplex. That would be that would mean that we had like two different connected components of the mapping space, flow framed empty to X. And my argument is that this can never happen. Because if you think about it, like what is even a flow by module from the empty thing to X? There is no data there. You can literally just write in a two simplex where this is the empty two simplex. And this is the empty flow by module between the empty flow categories. So it's just empty things everywhere. And this also works for higher and higher, like larger and larger simplices. I think like every time you have a flow n simplex which touches the empty flow category somewhere, then the interior becomes kind of degenerate. It just means that you can take the empty thing to be the interior. And of course, this also works for flow framed X to the empty thing. So these are contractible spaces because you can fill in any potential boundary of an n-simplex. Good. So that's out of the way. Let's think about suspensions. I'm gonna define two functors from flow frame to itself. I'm gonna call them suspension tilde because I mean we're gonna show that they actually agree with the suspension as computed by taking an actual colimit inside flow frame. But I want to kind of just write down a functor for now. And it's the following thing. It's defined by saying that everywhere you see one of these virtual vector spaces VP, I'm going to replace it with VP plus R. And that means that every time I have some kind of relation on some tangent bundle, I'm going to see a plus R minus R, and that's stably trivial, so I can just eliminate that. So this defines a functor. And likewise, I can do the inverse thing. I mean, I'm going to call it again with an inverse. It's not clear yet that it's actually inverse to the functor I wrote down above, but we're going to show that it is, and it does the opposite thing. It just removes an R. And I mean, if you want to think about this in a different way, just in terms of indices, which is like enough at this stage, you can just say that you take all your object sets and you just redefine the index to be kind of the old index plus one, or the old index minus one. You're just shifting all indices up and down, and that doesn't change anything. As long as you do it everywhere, right? Mapping from like some suspension X to something not suspended is not the same. But as long as I'm mapping from the suspension of X to the suspension of Y, it's the same. And this also tells us that this is a fully faithful functor, because everything that you could write down in some mapping space between these guys is just the suspension of something you've written down in the mapping space from X to Y. All right. So now the argument, or the hard proposition here, is that this kind of random functor that I've written down is actually suspension in your category. And we show that by showing that it satisfies the universal property you expect suspension to satisfy, right? Mapping out of a colimit is the same as a limit of mapping out of. So this is what you would expect the suspension to satisfy in terms of like after applying Yoneda. And it's enough to show that we have it's the right thing. And if I also can show like this thing down here, I've shown that my two functors were actually inverse to each other, and that gets me close to stability. So I'm not gonna prove this. It's like one of the theorems that I honestly don't understand. There's something super confusing here. But what I can kind of sketch for you is like a rough idea of why this works. The idea is the following. So I'm going to think about this equivalence, the top one. If I have a bimodule B from the suspension of something to something that is not suspended, I can do the following trick. I can pass back and forth from that to a 2-simplex that looks like this. So why is this the case? Like this 2-simplex, now I'm saying that B represents the interior of a 2-simplex. That means that like the stratum, some stratum like PS1 is the stratum that corresponds, like the object of the stratifying category that corresponds to BPS. Over here, in like this 1-simplex, B corresponds to the object of the stratifying category, which is just labeled by PS. But on this side, the tangent bundle of BPS, I mean, it's going to be something like VP, but it's VP plus an R because I've suspended once. And then it's minus VS, and it's minus R to the S for translation and some stabilization term. On this side over here, I'm going to get one extra R factor from the fact that I am now occurring in a family, and I can just identify that with this factor. So actually now it's in the interior of a 2-simplex, and I can just, in this 2-simplex, I'm just going to let all the other strata, so something like PS empty here, I'm just going to let that be empty. And then that's fine. You can have empty boundary strata. So this is like a categorified version of the statement that a closed n-manifold can also be seen as a bordism between the empty manifold and itself when you view the empty manifold as an n-1 manifold. So this is what we're doing, but it's categorified. And I think this argument is kind of convincing for why the homotopy groups, like based at the empty bimodule, are the same, but then actually constructing this as a map of mapping spaces is confusing to me. So I'm not going to get into that. Co-fibers. That's the last thing we need for stability. So given some flow bimodule from X to Y, we would want a flow bimodule that represents its co-fiber. And I'm gonna actually write down something, and then what Abusad and Bloomberg do is to prove that this does the right thing. And the formula here is, I want to say it's like a ripoff of the formula for the cone of a map of chain complexes. So you let C of B, this is my like candidate cone, or like candidate co-fiber. I'm gonna let it have the objects of X union the objects of Y. But I'm gonna take the index, or like this virtual vector space that's associated to each of the objects of X, and suspend it. So just add on an R factor. So if like some object P in X had the virtual vector space VP, then inside here it's going to be VP plus R. And I'm gonna use the following formula for the manifolds with corners that show up in here. I'm going to do X if both the objects were from X. I'm going to do Y if both the objects were from Y. And now it comes the trick. If P was from X and Q was from Y, I'm going to do BPQ. So BPQ, on the face of it, has like the wrong tangent structure to occur inside a flow category, right? It was actually a flow bimodule. but because X is now shifted up once, I can eliminate this extra R that comes from here with the missing R minus R factor from here. And if you sit down and write out what the boundary strata are here, you see that it actually has the correct stratification to be a flow bimodule or a flow category again. And it has kind of an obvious morphism, like an obvious bimodule into it from Y and an obvious one going out of it to X, which is just given by taking the identity on the relevant objects and 0 everywhere else. So that's at least like good. And like this composite is very clearly just the empty thing. Because like this kind of formal composite where I just take the product, it's always going to be empty. And it's like a bit of a tricky proposition, but you can show that this is indeed a cofiber. And I'm desperately running out of time, so I'm not gonna go into any more detail on that. Let me try to speed run the end here for like 5 minutes. Floor framed has small colimits. Like we have now shown that it has all finite colimits because we're stable and we have pushouts, right? So the trick is to say that we have arbitrary small co-products, and that's enough. So if I have some set S and I have some family of flow categories indexed by that set, I'm gonna just take the disjoint union over all of those. So that means the flow category whose set of objects is just the union of all the objects, and where there are no morphisms connecting between like these different indexing sets. And the fact now is that if I map out of something like this into something else, then this is given exactly by one morphism, like one bimodule out of each of these guys, which is a product of these spaces, which is the correct universal property for a co-product to satisfy. So by Yoneda, this disjoint union is a model for a co-product. And here it's important that this monoid gamma was 0. If this was not the case, then this would be something more complicated. So this is like maybe the only place in the entire paper where we use this. And this means now that we have all colimits. So like we have we're very close to showing that we have a presentable category. We need also to show that we have a set of generators. And in fact, we can show more. We can show that the flow category with one object alone generates the entire category. So let's show that it's compact first, like one is a compact object. That means that mapping out of that object preserves all colimits. And to show that, we know that mapping out of it is an exact functor just because of stability. So we just need to show that this guy also respects arbitrary or small co-products. So what is 2 seconds. Are we back? Can you see?
Yes.
Good, thank you. Now you could be kind of worried and say that again, this looks more like you're like a product again, that you're allowed to specify one map into each of these copies. But here, this fact that this union over all Q, so let's say I have some B in here. Then the union over all Q of B, the unique point in the flow category with one object, into Q has to be compact. So that
what do you mean by compact generator?
so there's a notion of a compact object in an infinity category, right?
Yes.
Yes. So I want to show that mapping out of this object commutes with all colimits.
Okay. Great.
And this is the only colimit that is missing. Because I have all the finite ones. Yeah. But what I'm saying is that you could be kind of worried that this would be like a product of flow framed 1XS, because you could be allowed to specify one map into each of the XS's. But the fact that this union has to be compact means that the morphism, a bimodule, is only allowed to touch a finite number of your S's. Which is why you can argue that this is in fact the coproduct of all the flow framed 1 to XS. And to see that it generates your category, I'm going to write any arbitrary flow category as a colimit of things starting all the way down with this. The way to do that is to filter your flow category by degree. If I start at some degree k, and I look at only the subcategory of objects only in degree k, this is something discrete. This is a disjoint, like a direct sum of copies of 1, maybe shifted up or down. Now this includes into the bigger thing of things in index k up to k plus 1, which goes into the things in index k, k plus 2. And all of these morphisms, like these bimodules that are implicit here, they're essentially given by the identity bimodule on the relevant objects. And if you look carefully at it, the associated graded of this is something like something like this. I just take in each degree, I just look at how many objects live in degree k, and I take shifted copies of the one object flow category. And like the colimit of this filtered thing is everything in x in degree larger than or equal to k. Now to go all the way down to infinity, like I would want, like all the way down to minus infinity as well, I'm going to do a kind of different thing. I'm going to argue that there are also maps from some k to infinity to x k minus 1 to infinity. And this might be surprising to you, because this is like not the natural thing to do. There is kind of also a natural filtration going the other way, which has a discrete associated graded. And that's what they used to argue in the paper, but I don't know if I believe their proof. So this is maybe a workaround. I mean, this associated graded is kind of horrible. I mean, it's like not that easy to describe. But what we know is that at every step, like the graded part that is here, is some flow category that has degree bounded below. Like there's the thing that goes in here can at most have objects. The lowest degree is k. And that means that I can construct them from this procedure up here. So the cofibers here are not going to be discrete things, but they're going to be things that I could write down using the procedure up here. And it converges in the colimit to the whole thing. Good. That means that one generates my category, both in the sense that everything is a colimit of it, but also that mapping out of that object detects equivalences. And that's what is also going to give us the comparison with spectra. Now we're using this like the full machinery of stable infinity categories, and in particular this theorem attributed to Trygve and Shipley, which tells you that if you have a stable infinity category generated by a single compact object, then mapping out of that object gives you an equivalence between your category and modules over endomorphisms of the generator. So then remaining thing is to show that the endomorphism spectrum of this generator is actually the sphere spectrum. Constructing this as a map of spectra is like a bit tricky, but we can see that it at least has like the right homotopy groups. Because if I want to see something in like pi n of this space, I should consider generators that look like this. Well, by module from a discrete thing to a discrete thing with one object, that's just a closed n manifold. So B is a closed framed n manifold. And like the relations I need to quotient out by is given by a homotopy between these guys. So that is something like this. If there's a 2 simplex like this, I should identify B and B prime. So I have like this edge is the identity on the one object flow category. So if we now write down what the stratification here looks like, we see that like H is honestly a framed Bordism between B and B prime. So the homotopy groups are at least the correct thing by Pontryagin and Tom. We know that the homotopy groups of the sphere spectrum are also Bordism groups of frame manifolds. So this gives you some indication. And like the work you have to do here is to actually write down. You can kind of think of this guy over here as being the infinite loop space of the infinite sphere, which is a co-limit of something you can control, and try to actually write down the map. Yeah, so there I'm gonna stop. Only 10 minutes over time. Hope that's not too annoying. Thank you very much.
Thank you very much. Great. So let's stop the recording.